What's up, guys? We were analyzing the batch reactor and we're going to use a first order reaction. We are going to be analyzing especially conversion. So they tell you, hopefully you remember, a batch has no inlets, no outlets, it has only generation and accumulation. So they tell you you have this first order elementary reaction, probably you are turning something A into products. You don't care about the products, you just care about this A. They tell you calculate the time needed to achieve certain conversion. Actually, not certain conversion, and then we're going to use this 90%. So let's do it. Our rate of reaction is here. Remember the negative sign here. And this is our constant. Remember, we got Arrhenius equations for that and all that. And concentrations here. Now let's substitute this in our design equation, which was this one here. You don't know where we got this equation, please go back one video and you will see where we got this. But essentially this guy here is the accumulation concept and this guy here is the generation concept. Now essentially we're just going to substitute this. Look how we have minus RA here, so minus RA here because we're going to input this value here. Perfect. So just take care about the negative sign. This one disappear because this is positive actually here. And let's pass this negative sign here. We have it here negative. Just remember that by definition the concentration of A at any moment or at any conversion is given by the multiplication of initial concentration of A, which is typically a data given, times 1 minus x, x being the conversion and x is generally between 0 and 1. So you cannot have bigger or larger quantities than initial concentration, and you can have lower as 0. So let's do it. We substitute that data here. Just remember, where is it here? Okay, concentration, initial concentration, final concentration, 0 to time here. Okay, we solve this analytic, this integral, sorry, here, and we need to substitute concentration of A at any moment and concentration of A at the initial conditions. This here, because K is a constant, you just take it away and remember that the integral of any value, which is a constant, in this case 1, is that constant, which is 1 times T, and don't forget to evaluate, which is essentially very easy, just a time. Now, this is just this value minus this value here. This is just substituting here and here. Okay, perfect. And if you remember logarithm rules, you can have natural logarithm of A plus, or let's say minus natural logarithm of B. You can have these also, and they mean exactly the same. And that's what I actually do here. Yeah, perfect. And if you remember, once again, sorry I didn't have it here, but by definition the concentration at any moment is given by the initial concentration times 1 minus x, which is the conversion. So I'm inputting this value here, and as you will see, this concentration or initial concentration will cancel with this initial concentration, and I will be getting this value here. The natural logarithm of 1 minus x equals this constant times time. Now we don't want this expression, we want to get just time, so we send this here dividing and we got our time. So it's pretty cool because this is a constant value. Actually you can find it in books or in the problem statement. It's a data, a number, x. So actually you could just find out how much time do you need to achieve certain conversion, and actually it is normal that it goes something like this. Actually we got some values. One thing I want to remark or to note you guys is that we don't need that initial concentration. So Ca of or initial moment, if I will give you 10 or if I will give you 1 or even if I will give you 0.01, let's say it's mole per liter, in each case it doesn't care, or this problem doesn't care because it's first order in a batch, it doesn't account for that. We do need the constant here, the K, which is 10 to the minus 4. Be sure that this dimension correct, and we're using this conversion. So the time needed to achieve that for this special reaction is 23,025 seconds, which if you change to hours, which will be divided by 360, you get 6.4 hours. So that is our first order reaction with our batch. Next video, we're going to see what happens when we have a second order batch reactor. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.